number 8, we have this stocking a fish pond problem. The ultimate the goal here first is to estimate the volume of the pond here, and they've given us some information in terms of the lengths of those cross sections of the pond, and ultimately if we use our trapezoidal rule here, we do have uniform subintervals, so therefore we can use our general formula. Right. And keep in mind that if we use that with the information that we're given here, we're ultimately going to have to figure out what our h is. And remember, h is b minus a over n, which ultimately is the length of the each interval, basically. So in this case, the length of the interval itself would be the lengths between the two, between each of the different bands that we have in the pond. So ultimately, each of these are 200 apart from each other. And again, that h is essentially that. It's just the length between the subintervals, which in our case would be 200. So ultimately, that part would be the 200 over 2. Yeah, that's a notation. You're right. Sorry, I forgot to get the 2 out of there. Thank you. All right. So ultimately, we have that, and then if we go through and we use our numbers in here, going from our first endpoint, left endpoint to right endpoint, then ultimately it would be 0, and then 2 times 520, 2 times 800, 2 times 1,000, 2 times 1140. 2 times 1160, 2 times 1110, 2 times 860, and then that endpoint being 0 again. And ultimately, what does that all turn out to be? How much? The answer to this is not the final answer. Keep in mind. Right.
Wait, why is h 200? Isn't h b minus a over n?
Which ultimately is the length of each subinterval. Their space. The spacing is 200. They're all 200 apart.
And then the length is 1600 because it's like there's 200, but there's 8 of them. So isn't that what b minus a is?
Remember, it's the vertical spacing is 200 feet between each of the.
Yeah.
So it's not 200 total divided by 8. It's 200 between each of those red lines that we have.
Yeah. And isn't b minus a just over the interval?
Well, the interval, in terms of the spacing part, I mean, it would be each one of those would be 200, so it would actually be 1600 total divided by 8, which would be 200, because there's 8 subintervals. So that's why the b minus a would be the 1600 part. The n would be the number of subintervals, 8, which ultimately gives us h equals 200. So that's why we have 200 over 2. All right. So the the final answer here, keep in mind, is I don't have it on my book here, but you said it was what? How much? 1 million something?
1,318,000.
All right. So that total right there is the 1,318,000. Okay. Now keep in mind what we've calculated here though is something essentially it's 2-dimensional. Okay. And if it's 2-dimensional, then that's not really a volume here, because there's one other piece of information they told us is that the average depth of the pond is 20 feet. So ultimately we want to think of the pond as essentially like a prism, okay, where the shape of the base is, it really doesn't matter, it could be any shape. In this case it's a shape that we don't have a geometric formula for, but ultimately if we can figure out the surface area, which is what we just did right here, okay, we ultimately calculated the surface area of that pond, okay, and then we multiply it by the depth of the pond, if you will, considering it just a prism with an average depth of 20 feet, then ultimately we're going to take that number and we're going to multiply it by 20, because that's the depth. And keep in mind, this would be feet squared, this would be feet, and ultimately the final answer then would be 2,000,000 and 636 feet cubed.
Yeah, you got more.
And again, what we've calculated in the trapezoidal rule part is just the surface area of that pond. Okay? And ultimately, if we want to get a volume, okay, it's again treated as a prism. If we had a shape that had that as its base, okay, and it had an average depth of 20 all the way around, okay, ultimately it would be treated as a prism, and we'd find the area of the base times the height, and the height being the depth, which would be 20.
Yeah, you don't want to put decimals, 26,000.
Oh, whoops. This was 1 million? Oh, it's times 20. Sorry.
Yeah.
So 26,360,000. There. Should be right now.
Yeah.
Look good? Alright, so ultimately that would be the way we would calculate an estimate for the volume of that pond. Okay. And in part B here, it says you plan to start the season with 1 fish per 1,000 cubic feet. So let's deal with that first. If we want 1 fish per 1,000 cubic feet, then if we multiplied our cubic feet that we have in this pond by 1,000, wouldn't that tell us how many fish? If I do cubic feet divided by fish per cubic feet, so how many fish?
26,360.
So we get 26,360 fish would be the total fish that we'd put in the pond. Okay, so we're going to start the season with that. And it says that you intend to have at least 25% of the opening day's fish population left at the end of the season. Okay, so we want 25% of that left. So ultimately, if I did 26,360 times 0.25, then ultimately how many fish would I want to have left?
Well, that's 6,590.
6,590. All right, and so that means that the question then is what's the maximum number of licenses the town can sell if the average seasonal catch is 20 fish per license? Okay, keep in mind this is how much we want to have at the end. That means we want to catch the subtraction of these two. So how many fish do we want to catch altogether? 26,360 minus 6,590. 770. So we want to catch that many fish, so we'll catch this many. And it says that we can catch 20 fish per license, and the bottom line is how many licenses do we need to sell, so we'll just divide this by 20. 938. 988. Should be 988. 18,770.
Supposed to be
19,770 is what this is supposed to be, sorry. So 19,770 divided by 20, so it should be 988.5. Alright, so bottom line here though, keep in mind though that we want to have at least 25% left. So how would we want to round this then, you think? Yeah, we didn't want to round it down because if we sold 9.99, we would catch more fish and we'd have less than 25% left at the end, wouldn't we? So we actually want to round down to 988. All right. Questions on any part of that one? Excellent AP question. Now that you've seen it work, it's hopefully not terribly difficult. Got a couple steps. All right, what else from our homework assignment? Mike?
Number 10.
Yeah, number 10, we have an integral that we have to use Simpson's rule for. And ultimately the integral that we write here for -1 to 3 of f of x dx, and in this case our f of x, we know f of x, it's they gave us the actual function here, x cubed minus 2x dx. Alright, and ultimately if we want to use Simpson's rule here, we know that our Simpson's rule is going to be h over 3, and h being the subinterval length, and our n value here, keep in mind, is 4, so that means our b minus a is 4, and our n is 4, so that means our subinterval length will be 1. So we would have 1 over 3 here when we start filling in our blanks, and we know that's y sub 0 plus 4, y sub 1, etc. So ultimately we need the y value at our left end point, and our left end point being -1, we would put in -1 in here, and we get -1 plus 2, which would be 1. And then 4 times the 0 in there would give us 0. And then 2 times 1 in there would give us 1 minus 2, that's -1. Putting a 2 in there would give me 8 minus 4, which is 4. And then finally the left end point in there would give me 27 minus 6, which would be 21. So the setup would look like that for the Simpsons rule setup, and then from there we would just calculate. Inside we'd have 1 minus 2, that's -1, and 16, that'd be 15, and then 15 and 21 would be 36. So ultimately the answer would be 12. So that would be our approximation for the area under that curve using Simpson's rule. And then part B says find the exact value of the integral. And so if we want to find the exact value, we will integrate. And so if we integrate from -1 to 3 of x cubed minus 2x dx, we'd find the antiderivative x to the 4th over 4 minus x squared. And calculate the 3 in there. Whoops, x to the 4th over 4, right? So if we put our 3 in there, we're going to get 3 to the 4th power, which is how much? Oh, 81. So we'd have 81 fourths. So 81 fourths minus a 3 in here would be 9. And I'm just going to write it as 36 fourths here. I'm going to put the 3 in there, 9. So I'm going to subtract those two. And then minus, if I put a -1 in here, I'm going to get positive 1/4 minus 1, which would be 4/4. Everything in fourths here, we can get an answer for that. So ultimately in the top, in the first part here, 81 minus 36 is going to be 45. So 45 fourths minus, and in the parentheses here we got -3/4. Which ultimately gives us minus would give us 48/4, which ultimately gives us 12. So what did we just find here? What happened? Well, they're equal. The Simpsons rule approximation gave us the exact area, didn't it? Alright, so in considering that further, in part C, they asked us to explain how you could have predicted what you found in, oh, nope, forgot part B. Or part 2 of part B, if you will. What is the error? Well, the error is going to be 12 minus 12, which is ultimately what? 0. So the error is 0. And so the part B here says, explain how you could have predicted what you found in part B, knowing the error bound formula. Okay, what I want you to look at next then is, we'll go to another page here. So I'm still working on number 10, part C. If we look at the error bound formula for Simpson's rule, remember I talked about that the error bound formula is b minus a over n, or not n, 180, and then h to the 4th, and then m of the 4th derivative. So that being our formula, if we want to know the error here, we know the error has to be less than this stuff right here. Ultimately, this stuff right here, this really don't matter, because ultimately, remember, our function in question was x cubed minus 2x, wasn't it? This was our function, and that m value right there is the maximum value of the 4th derivative. Cool. And ultimately, if this is my f, what's f prime? 3x squared minus 2. What's f double prime? 6x. What's f triple prime? It's 6. And what's f 4? 0. So ultimately, no matter what this stuff is, what is this? It's 0 times something, and that equals what? 0. So could we have predicted that knowing the error bound formula? Could we make a more of a generalization on that? As long as we have anything that's a power function that's cubic or a lesser degree, then what's the error going to be when we use Simpson's rule every time? 0. Okay. Simpson's rule will give us the exact area every time, as long as I have a polynomial that's less than degree 4. So anything third degree, second degree, first degree, constant. Alright, and then finally in part D says, is it possible to make a general statement? Well, I guess we just did that, didn't we? So part D would be, so any polynomial degree less than 3, or less than 4 I should say. So any polynomial of degree less than 4. The error is going to equal 0. Another general statement. And they said in general about cubic polynomials, well, a cubic polynomial would qualify for that then, wouldn't it? Degree less than 4. Alright, questions on that one? Others so far? Okay. 17, we need the calculator program, so we'll have to get the calculator program before we can do that one, so just hold off on that one for the time being. Alright, just so we're clear, we're gonna do two things right now. I'm gonna give you your quizzes back from last week, and